touch the leg, everybody. So today I'm going to start the last part of this chapter, and normally I divide this chapter into three parts. First part is potential, then second part is potential energy, and the last part is what we call as capacitance. Capacitance. So before I start this topic, what we would like to study is we would like to recapitulate few important concepts like potential. All right, and we talk about potential. So we say that potential, we define potential as V. V is what we define as, this is how we define V, and charge creates the electric field, and then the electric field can be represented in terms of a scalar quantity, which we call as a potential, and which is what we call as work done on a unit charge. When I talk about electric field, it is force on a unit charge. Electric potential is work done on a unit charge. Alright, this is the potential. So whenever there is an electric field, there will be a potential difference, and this is how we define potential and electric field relations. Potential is equal to Vg. This is the relations we found between a potential and electric fields. This is very important relations. Alright, so now what I am going to do is first I would like to study the effect of electric fields. If I apply electric field across conductors, what is going to happen? If I apply electric field across dielectrics, then I'm going to define what exactly dielectric is, and then what is going to happen, right? So now let me have a very rough difference between the dielectric and conductors. So conductor is the one which has so many free charge carriers, alright, and dielectric is the one which doesn't conduct electricities. The reason is that it has no free charge carriers. Also, so dielectric is the one which has no free charge carriers, so therefore it doesn't conduct electricity, and conductor is the one which has free charge carriers, so therefore applying electric field, conductor can conduct electricity. So this is the difference. Alright. So now what I'm going to do is, now I would like to find the differences between a dielectric electric fields by a dielectric and conductor by applying electric fields. So first, this is a conductor. Let's say this is a conductor which has infinite number of free charge carrier. You have learned this in the lower class. Now, if I apply external electric field, right? So this is E naught is an external electric field, and apply conductors. All right. As soon as you apply electric field inside the conductors, there will be a movement of a charge carrier, that is electrons. So electron goes in the direction opposite to electric fields. So electron leave this side and start accumulating at this side. So this side would be a negatively charged sides, and once the electron leave this surface, this creates a positive charge. Once the electron leave this surface, this will create a positive charge. So this is what we call as positive charge surface. Now the point is how long this movement will take place. Alright, so the movement will go on until this external electric field and induced electric field. This is the electric field induced by two charge, alright, positive charge at this side, negative charge that side. This will create a electric field, alright. Positive charge at this side, negative charge at other side will create a electric field. This is what we call as induced electric fields, and this is an external electric fields. So the flow of a charge continue until induced electric field. I say induced electric field is equal to external electric field. So once the induced electric field is equal to external electric fields, then the flow of free charge carrier will stop, and net electric field inside conductor remain 0. So therefore we say that net electric field inside conductor will remain 0, alright, after within a very short period of time, and you will see a negative charge at this side and positive charge at that side. So therefore when you apply electric fields, alright, depending on the strength of electric fields, there will be a positive charge at one side, negative charge at the other side, and electric field inside conductor remain 0. Alright, so this is what we have in case of conductors. Now the point is, what about dielectric? When I have a dielectric, since dielectric has no free charge carrier, what happens is that this is the external electric field, and when I apply external fields, yes, this external electric will create a negative charge surface at this side, positive charge surface at that side. However, electric field due to these two charge surface, what we call as induced electric field, is always less than external electric field. So this is how I can write like this. This is always less than this. There is no flow taking place. There is no flow of electron taking place. There is no flow of a charge carrier taking place. And this is what we are going to study now. Alright. And there will be a charge surface created on the other side. Alright, two sides. And this is what we normally call as a polarizations. Alright. And because of these two charge surface, we will be having induced electric fields. And this induced electric field is always less than external electric fields. So therefore, net electric field is not 0. Net field is not 0. Net electric field is not 0. However, net electric field is less than applied externally. So that therefore the difference is that in case of a conductor, net electric field reduced to 0. However, in case of a dielectric, net electric field reduce, alright, but never become 0. Alright. So the stronger field you apply, then induced electric field becomes 0. However, electric field inside dielectric will never remain 0. Why? Because there is no flow taking place. Polarization is taking place inside dielectric. So the detail I'm going to do now, right? So now next I would like to do more on dielectric. So therefore, just now I defined that dielectric is non-conducting materials which does not conduct electricity and which has no free charge carriers. So normally dielectric of two kinds, polar dielectric and non-polar dielectrics. Alright. So the polar dielectrics examples are HCl's, H2O's, and these are the polar dielectrics. And non-polar dielectrics are nitrogen molecules, carbon dioxide, oxygen molecules. These are the polar. Now the point is, what is different between them? Maybe the detailed discussion may be done in the chemistry. Alright, just for our understanding, polar dielectric is the one which has each molecule has net dipole moment. I say each molecule has net dipole moment. Each molecule has net dipole moment. But overall bulk net dipole moment is 0. But overall, alright, it has 0 net dipole moment. This is the point. And non-polar dielectric, that means each molecule has no dipole moment. Each molecule has no net dipole moments. The reason is that when we talk about polar dielectrics, the center of a positive is not coincide with the center of negative charge. All right, there is a separation of positive charge and negative charge. There is a separation of positive. Therefore, in chemistry, we say the partial positive, partial negative. There is a separation. All right. So therefore, we say that the center of a positive charge is not coincide with the center of a negative charge. So therefore, there is a separation of a positive and negative charge, which led to dipole moment. All right. However, in case of a non-polar dielectrics, center of a positive exactly coincide with the center of negative. All right. So leaving a zero distance between a partial positive and a negative. So therefore, which has zero dipole moment. So that means this is how we represent, right? So polar dielectric, this is how we represent. This is how we represent. This is a polar dielectric. So there is a separation of a positive and negative taking place, and this is a non-polar. There is no separation. They coincide. These two doesn't coincide. Centers of a positive and a negative doesn't coincide, and so therefore this has a net dipole moment each molecules, and the center of a positive and a negative charge coincide. The separation is zero, so net dipole moment is zero. So this is the differences between polar dielectric and non-polar dielectric. All right. So the detailed study about polar and non-polar is done in chemistry, right? So this is what I have. Now what I'm going to do is, what about if I put a polar dielectric, right? So I told you that this is a bulk. This is a bulk, right? So all polar dielectric has zero net dipole moments. Zero net dipole moments. Zero net dipole moment. Why? Because each dipole moments, right? They cancel each other, right? So you have so many molecules in a bulk. So therefore, one molecule, the dipole moment of one molecule cancel out with the dipole moment of another molecule. So therefore, overall there is no dipole moments. Overall net dipole moment zeros. So this is when we don't apply external electric fields. When we don't apply external electric fields. So in absence of external electric field is zero. When we don't apply external electric fields, so the net dipole moment even in case of polar molecules are zero. So you see a net dipole moments. You see a net dipole moments. However, all dipole moment is zero. Then electric field is zero. All right. Now, when I apply electric fields, when external field is applied, then what is going to happen is a reorientation takes place. So each molecules align themselves. Each molecule align themselves such that the positive charge goes to a negative side. Positive charge try to align along the electric field. Negative charge try to align opposite to the external electric field, so that you find some arrangement. This pattern shows you that there is no random. This is a random pattern. This is a random. However, look at here. This positive charge are along this side. The negative charge side are along this side. So therefore, you will have a net dipole moment. So because of this, all right, alignments. So you find a positive charge surface at one side and negative charge surface at other side. However, the net electric field is not zero, that we have discussed just now, right? So therefore, this is induced electric field. This is the electric field due to positive charge surface at this side and negative charge surface at other side. And this is external electric field. Look at here. Induced electric field and external electric fields are opposite. Look at here. This is an external electric field. We apply external electric field in one direction and then induce electric field in other directions. So therefore, what we have, this is induced electric field, this is external electric field, they cancel each other. However, since the external electric field is more than induced electric field, you will be having net electric field which is less than external electric fields, which is less than external electric field. This is what I have, right? So, because of reorientations or the alignment of each molecules along external electric fields, this create positive charge surface at one side and this create negative charge surface at other side. Alright, and this overall this creates net dipole moment. So overall you will be having what we call as net dipole moment. Overall this creates net dipole moment. Overall this creates net dipole moments. Why? Because you have a positive charge at this side and a negative charge at the other side. Alright, because of which electric field inside dielectric would be less than external applied electric fields. Again I am repeating this. Because of which electric field inside dielectric would be less than applied external electric field. So this is what I have. And then so this is for polar, this is the textbook diagram. This is the textbook diagram. So now I think you don't need much explanation here. So I told you overall net dipole moment is 0. Net dipole moment is 0. Net dipole moment is 0. Overall net dipole moment is 0 if external electric field is 0, apply external electric field 0. However, each molecule has net dipole. Look at here, each molecule has. And you see the dipoles are in the random directions. Now look at your dipoles. These dipoles in this direction, this dipole in that direction. So you have random dipole movements. Each molecule has different dipole moments, so therefore they cancel each other. The net dipole moment will be 0. Now, when I apply external electric field, this external electric field is non-zero. Then what happens is that again I say reorientation will take place. Molecule themselves align along external electric field, and this creates what this creates? This creates net dipole moments. Net dipole moment, and this is what we call as polarization taking place. So this is for polar dielectric. And now non-polar dielectric we have. This is a non-polar dielectric. For non-polar dielectrics, without applying external electric fields, net dipole moment is 0, no doubt, but because each molecule has a 0 net dipole moment, right? If this is 0, alright, then obviously net dipole moment is 0. Net dipole moment is 0. Because each molecule has 0 dipole moments. Now when I apply external electric fields, then this is non-zero, then E is non-zero, then what happens is a stretching. Alright? Stretching of a molecule taking place. If electric field is along these directions. Alright. So look at here, I will just give you one. Since electric field is in this direction, positive charge goes in this direction, negative charge goes in that direction. So therefore, dipole is created. Alright. Before applying external electric, each molecule has 0 dipole moments. Once you apply external electric fields, positive charge goes in this direction along external electric field, negative charge in opposite directions. So the dipole is created. So each molecule has now net dipole moments, and the dipoles are placed such that positive charge is along this side, negative charge along the opposite sides. So now you have, this will create, I just say, net dipole moment. This will create net dipole moment. Net dipole moment, right? So this is the difference. The final part remains same for both polar and non-polar. Initial, without applying external electric fields, then for non-polar, each molecule has zero net dipole moment. So this is what I have. Now look at here. Now therefore, what happens if I apply an external electric field, right? If external electric field is applied to a dielectric, what is going to happen now? It says the polarization will take place. This is the overall conclusion, right? Polarization will take place. Alright? There will be electric field, alright, there will be a net electric field inside. Alright? So we'll be having an induced electric field, external electric fields. So therefore, when external electric field is applied across the dielectrics, there will be a polarization. Alright. And the strength of the amount of polarization defined by two factors. That is, one is the strength of dielectric, strength of external electric field, and the second part is the nature of dielectrics. Second is the nature of dielectric. Alright. So what do you mean by polarizations, right? So when I say it is polarized, that means this bulk molecule has net dipole moments. So the polarization is defined as net dipole moments. Net dipole moments defined as net dipole moments. That net dipole moment per unit volumes. So that means each volume has net dipole moment. Each volume of a molecule has net dipole moment. So this is what we have. And a polarization is a vector quantity. Polarization is a vector quantity, and so therefore polarization is proportional to external electric field. This is normally for linear dielectrics. I'm not going to talk much about what exactly linear dielectric. So this is a very important relations. Alright. So the polarization is all defined by external electric fields. Now if I remove a proportional sign, this is the chi-Greek letter. Alright. This is the nature of materials. This is what we call nature of dielectric. And this constant is what we call as susceptibility. Electric susceptibility. This constant is what we call as electric susceptibility. Alright, this is defined by a nature of material. Right? So this is what we have. Alright. So polarizations is directly proportional to the externally applied electric fields. More the field is applied, greater will be polarizations, and the nature of material is defined by susceptibility. This is what we call as a chi. Greek letter chi, right? So this is what we have in case of. So therefore, all what we are going to get is, this is what we are going to get it, right? So all, when I apply external electric field to a dielectrics, you will be getting this is negative surface charge. This is density. This is positive charge surface. Positive charge surface. This is a negative charge surface. Alright. This is and then this cancel out, this cancel out, this cancel out, like this. All cancel out. So you can't say this is a positive charge surface. Why? Because this all can get cancelled out. So therefore, overall what we are going to get is, we'll be getting a one side a negative charge surface, and other side we'll be getting a positive charge surface, and this is defined by a negative charge surface density, this polarization, right? This is defined by positive charge surface density. So this is the final point, right? So if I have a dielectric slabs and put in the external electric fields, so we will be getting some positive charge surface at one side, negative charge surface at other side, and we define the polarizations, and then because of which, all right, electric field inside dielectric would reduce. All right. So this is what we have in case of dielectric. All right. So this is what we are going to apply now in case of electric. In case of capacitor. So now what I'm going to do is I will do what we call capacitors and capacitance. Capacitors or capacitance. Alright, so this is capacitor. So first my topic is capacitors. So what exactly capacitors? Maybe this is new to you, right? So we say capacitor is what we define as, this is a system of conductors, let's say two conductors. It is a system of two conductors, two conductor separated by, let's say, insulating mediums. This is what we call as a non-conducting mediums. So this is what we have. A system of two conductors separated by insulating mediums is what we define as capacitors, right? So this is conductor 1, this is a conductor, this is conductor 2, and these two are separated by insulating medium, could be here, let's say this is here. And this become capacitors, right? So what is the role of here? What is the role of dielectric mediums, or what is the role of insulating mediums? That this medium will never allow a charge from first conductor to move to a conductor 2. Since this is the insulating mediums, this will stop a movement of charge from one conductor to another conductor. This is the role of insulating mediums. Again, I am saying the role of insulating medium is to stop a movement of charge from one conductor to another conductor. Because of which there will be a positive charge at one side, then there will be a negative charge at other side. So this is what we have. All right. So this, and now what I'm going to do here is I have two conductors, conductor 1 and conductor 2, separated by some insulating mediums. And I say that conductor 1 has a positive charge Q. This is conductor 1. And conductor 2 has negative charge. And these two are separated by dielectric mediums. And I say that the conductor 1 has potential V1. And conductor 2 has a potential V2. With the potential difference, that is, let's say 1, 2 would be equal to 1 minus 2. This is the potential difference. Let's say potential difference is V. And what is the charge? Normally, when we talk about capacitor, charge on one side is equal but opposite with another conductor, right? These two are Q and Q's are equal and opposites. Normally we see, right? So therefore, this is going to be a potential difference. This is a potential difference. This is a potential difference across gate. This is a potential difference create across gate. All right. So now look at here. Now what I'm going to do? Now I'm going to define what exactly, right? So look at here. And this V, the potential difference across the conductors, across the two conductors, is proportional, right? Is proportional to charge. Alright? If a more charge on two sides, alright, of a conductor, then the greater would be a potential. This is the point. Greater would be a potential. So this is something like that. If I increase the potentials, then charge would increase. Or if I increase the charge, then the potential would increase. These two are, one another, right? So again I say that Q is again proportional to V. Q is also proportional to V. If I go on increasing V, and Q has to increase. There is no other way, right? So therefore we find a relation. What we are going to find out is we are going to find a relationship between V and Q of two conductors. V and Q of two conductors. So normally relations are nothing but constant proportional relations. The relations are nothing but constants, and relations are nothing but constant proportionality, right? So therefore what I say is that V, alright, so I remove this proportional sign and I put some constant. This is some constant, this is some constant. I record it as a constant proportionality. Proportionality constant. So this is some constants. So this is some constants which does not depend on Q, which does not depend on a V, which depend only on a nature of mediums, the nature of these two, the geometry of these two conductors, right? So this is what we have, and I say that this C constant is defined as Q by V. So this C constant is what we call as capacitance. This C is what we define as capacitance. Capacitance. So this is what I have. So what is capacitance? This is how we define. C is equal to Q by V. And it's, when I look here, C depends on a Q and C depends on a V. Yes, this is also right. Why? When I increase a V, a Q, V also has to increase. So therefore, C, capacitance C is independent of Q and V, independent, right? C does not depend on V, C does not depend on a Q, and C is defined by mediums, dielectric mediums, and C is also defined by geometry. Two conductors, geometry of two conductors. Geometry of two conductors. That means C is constant proportionality. So constant proportionality are not supposed, not depend on a true quantity, right? So this is what we have. So C is a constant which we call as a capacitance, and which depend only on the mediums, nature of mediums, and the geometry of two capacitors. Alright. So this is C is what we call as capacitance. So look at here. Now I'll define what exactly C is. So C is what we call as Q divided by V. This is defined as charge per unit potential difference. This is what we say, charge per unit potential difference. Charge per unit potential difference. Alright, so that means to apply this much amount of if I apply this much amount of potential, then how much charge should be? Alright, so how much charge should be in order to have this much potential difference? So this is what we call as a capacitance. This is what we call as capacitance, right? So this is the property of, so capacitance is a property of capacitors. Capacitor has capacitance. We have done in the lower class, resistor has resistance. Likewise, capacitor has capacitance. Alright. So this is what we have. So capacitor is charge, capacitance is what we call as charge per unit potential difference. Alright. Now, SI unit of capacitor is, capacitance is, SI unit is ferrite, normally defined as F, which is what we call as 1 coulomb per volt. This is what we call as 1 coulomb per volt. So I will define what is 1 farad. This is the big unit. 1 farad is extremely big unit. So 1 farad is defined as, look at here, this is very essential to define a unit, right? So the concept, if we could define this unit, then somehow we could be able to understand the concept behind capacitance, right? So this is defined as 1 coulomb of charge exists across the potential difference of 1 volt. So 1 volt is not big, and 1 volt is so big. So 1 coulomb of charge, let's say this is 1 coulomb, positive, this is 1 coulomb, and this potential difference is 1 volt is what we define as 1 farad. So therefore I say 1 coulomb of charge exists under a potential difference of 1 volt. 1 coulomb of charge exists under a potential difference of 1 volt is what we call as 1 farad. This is a very, very big unit. Alright. And now again, the question is how long we can put on charge, right? So therefore when we talk about capacitors, what capacitor does is store charge. Capacitor store charge. Once the capacitor store a charge, alright, there will be a potential difference and then they will create an electric field in that space, right? Capacitor store a charge due to which there will be an electric field across a space or in that particular space and there will be a potential difference. These two are related, right? Now, my point is, capacitor has a limit. You can't go on and accumulate charge on two sides. Alright, this is what we call as dielectric strength. We say that dielectric doesn't conduct electricity. This doesn't mean that this will not at all going to conduct electricity, right? So this is one. So two capacitors, these two charges can hold a charge, can accumulate a charge across two sides, unless and until, alright, electric field, right? Unless and until electric field is less than dielectric strength. Less than dielectric strength. Less than dielectric strength. This is one. So what is dielectric? Dielectric strength is, this is the maximum electric fields. This is the maximum electric field that dielectric can withstand. If you apply an electric field more than dielectric strength, then dielectric no more strength withstands electric field, hence it conducts electricity. That's one very important point, right? So every time you have to keep electric field below dielectric strength. Alright. So dielectric strength. So this is dielectric has a limit. The limit of a dielectric is the dielectric strength. So you can't go on and put an electric field more than dielectric strength. If an electric field is more than dielectric strength, so then dielectric does not act like dielectric. Why? Because it will conduct electricity. Alright, so therefore this is very important. So therefore when we talk about air has a dielectric strength. Air medium has a dielectric strength 3 into 10 raised to the power 6 volt per coulomb. This is the dielectric strength of air. Alright, so I cannot apply electric field more than this. If I apply more than this, then it will conduct electricity, right? This is exactly what we find in case of lightning and thundering, right? When you see that you conduct electricity during a thundering times. During lightning and thundering times, what happens is that the electric field across the cloud becomes so high that it conducts electricity, and you see the current, or you see a movement of charge in a sky. So this is what we have. So therefore, every time we have to maintain electric field, across the conductor below dielectric stance. Alright, so this is all about dielectric. So now what I am going to do is, we are going to do parallel plate capacitors. Parallel plate capacitor. So we are done with the capacitors, now capacitance. Now I am going to do parallel plate capacitors. So this is, we can have different kinds of capacitors. So the capacitor that we are going to discuss in this textbook is parallel plate capacitors. So we are going, the aim is to get capacitance. We say that capacitance does not depend on a charge. Capacitance does not depend on potential difference. Capacitance depends only on the nature of readings and geometry of conductors. Alright. So first what I'm going to do is, I have two parallel plates. I have two parallel plates of area. Two parallel plates of area A. This is area is A. Alright. Two parallel plates of area A, and the distance of separation is G, and this is very small. Distance of separation is very small, and I say small. And how much small, right? That small. What about the distance should be, right? How much distance should be? Distance should be, let's say, it should be very small compared to area. So therefore, the area is going to be huge. And the distance of the distance is going to be, distance between two plates is going to be very, very small. This is very important. This is very important relation. Alright, and I say that plate number 1 has positive charge surface. Plate number 2 has negative charge surface, and you have electric field E. Electric field between plates. Electric field between a plates, and I say V is a potential. Potential difference. Alright, I say a potential difference between the plates. So now what I'm saying, now we say that this two plate, very important approximation, right? Two plates, I say two charge plates. Two charge plates act as infinitely thin plates. Act as infinitely uniformly thin charge plates. Uniformly charge plates. This is very, very important approximation. Why? How can I take these approximations? This is the reason, right? So therefore, because of which now I am going to do this. Alright, electric field created by a plate number 1 is going to be, this is the electric field created by a plate number 1, and electric field created by plate number 2 is going to be, let's say plate number 1, I just say plate number 1, Electric field created by a plate number 2 is going to be, alright. Can I then make this is minus. This is just a recapitulation of class the previous topic. Now I'm going to choose the 3 regions. I'm going to choose the 3 regions. Alright, region 1, region 2, region 3, and try to find out electric field, total electric field in each region, right? So let's say first region number 1. This is region number 1. What is electric field inside region number 1? Region number 1. I'm right here. Electric field due to the plate number 1 is going to be, look at here. This is plate number 1 is going to be this. Electric field positive charge is going to be sigma by 2 epsilon naught. This is electric field. Why? Because positive charge is outward. And electric field due to plate number 2 is going to be sigma 2 epsilon naught is the points. Alright, why? Because this is inward. This is inward. Alright, here it is inward. This is outward. Why outward? This is a positive charge. Why inward? This is negative charge, right? So therefore, what about that electric field? Region number 1. So I just write region number 1. Electric field would be equal to sigma divided by 2 epsilon naught minus sigma by 2 epsilon naught. Field would be 0. This electric field is 0. Net electric field is 0. What about region number 2? Region, like I write here, region 2 we have here. What about electric field due to positive charge? Sigma epsilon naught, this is again outward. I'll use blue pen. Blue pen has positive charge. Sigma 2 epsilon naught outward. Then sigma 2 epsilon naught inward. Alright, and then total electric field would be zero. Now, what about third region? This is the third region. Let's say third region. This is sigma divided by 2 epsilon naught. This is outward. And so again, I use the blue pen. Sigma 2 epsilon naught outward. Sigma 2 epsilon naught inward. Now look at here. Region number 3. Region number 3 has electric field is going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught sigma by epsilon naught. Alright, they are in all same directions. Alright, this is electric field. This is the electric field inside capacitance. This is the electric field inside 2 parallel plates. This is the electric field inside 2 parallel plates. So we found our electric field. So now electric field is going to be this. Now, what is potential difference? We say that potential difference is what we define as this. E into D, and therefore we call it as sigma by epsilon naught D. And what is sigma? Sigma is going to be charged by area, right? So therefore charged by area, this is a sigma. Alright. Now let's define the potential capacitance. What is capacitance? Capacitance is a charge per unit at potential difference. Charge per unit potential difference. Charge, and I substitute here QD divided by epsilon naught A. Q2 cancel out. Finally we get epsilon naught E by 2. This is the final expression. Alright. So the final expression we have is C is equal to epsilon naught A by T. This is the final expression. Alright. So now look at here. Looking at these expressions, capacitance is not defined by a charge and a potential. This is the area of a true plate, and this is the distance between a true plate. Alright, and this is what we call as permittivity, electric. And this is all meaning. Permittivity is nature of meanings. So this is what finally what I have is, so capacitance is equal to epsilon naught A by T. This is an expression for capacitance. Alright, so this is how we derive capacitance of parallel plate capacitance. Alright, so now what I'm going to do is, we would like to see how big 1 farad is. I told you 1 farad is very, very big. So let's measure our area of let's say find area of a plate having capacitance 1 farad. Okay, let's say the distance of separation is, let's say, 1 centimeter. So I put 1 centimeter, it's 1 centimeter, right? So look at here, and then the capacitance is 1 farad, and this is epsilon naught is electric permittivity. The value of electric permittivity is going to be value of electric permittivity is 8.854 into 10 raised to power minus 12 coulomb square per meter square. And now I see a 1 farad capacitance having a 1 farad, and epsilon naught area I don't know, we are going to find out. Distance is 1 centimeter. Okay. And then area must be equal. Now area must be equal to 1 centimeter is 10 raised to minus 2 meter, and then divided by 8 into 8.854 into 10 raised to minus 12. Let's say this is almost 10. So this is equal to almost 10, then this is equal to 10 raised to 11. Alright, it goes out 10 raised to 9, right? Meters square. So this, look here. If I choose, let's say if I take a capacitance of 1 farad, then the area of a parallel plate should be this much. This is extremely very big. 10 raised to 9 meters square. 10 raised to 9 meters square is a huge area. So it is not practical, right, to get a capacitance of 1 farad. So therefore, normally capacitors of microfarads, capacitors of picofarad. Alright. So this is all about capacitance. Thank you.